Load balancing revisited, a more advanced LP application. In this section, we consider a more general load balancing problem. We will develop an approximation algorithm using the same general outline as the two approximations we just decided for vertex cover. We solve a corresponding linear program and then route the solution. However, the algorithm and its analysis here will be significantly more complex than what was needed for vertex cover. It turns out that the instance of the linear programming problem we need to solve is, in fact, a flow problem. Using this fact, we will be able to develop a much deeper understanding of what the fractional solutions to the linear program look like. And we will use the understanding in order to route them. For this problem, the only known constant factor approximation algorithm is based on routing this linear programming solution. The problem we consider in this section is a significant but natural generalization of the load balancing problem with which we began our study of approximation algorithms. There, as here, we have a set J of n jobs and a set M of n machines, and the goal is to assign each job to a machine so that the maximum load on any machine will be as small as possible. In the simple load balancing problem we considered earlier, each job J can be assigned to any machine I. Here, on the other hand, we will restrict the set of machines that each job may consider. That is, for each job there is just a subset of machines to which it can be assigned. This restriction arises naturally in a number of applications. For example, we may be seeking to balance load while maintaining the property that each job is assigned to a physically nearby machine or to a machine with an appropriate authorization to process the job. More formally, each job J has a fixed given size Tj, which is greater than or equals to 0, and a set of machines Mj, which is a subset equals to M, that it may be assigned to. The sets Mj can be completely arbitrary. We call an assignment of jobs to machines feasible if each job J is assigned to a machine I in Mj. The goal is still to minimize the maximum load on any machine. Using Ji, which is a subset equals to J, to denote the jobs assigned to a machine I in M in a feasible assignment, and using Li, which is equals to the summations of Tj, summing for all J in Ji to denote the resulting load. We seek to minimize maxima of Li where the maxima is taken among all the possible index I. This is the definition of the generalized load balancing problem. In addition to containing our initial load balancing problem as a special case, setting Mj equals to the whole M for all jobs J, generalized load balancing includes the bipartite perfect matching problem as another special case. Indeed, given a bipartite graph with the same number of nodes we can view the nodes on the left as jobs and the nodes on the right as machines. We define Tj equals to 1 for all jobs J and define Mj to be the set of machines. Nodes I such that there is an Hij in E. There is an Hij an assignment of a maximum load 1 if and only if there is a perfect matching in the bipartite graph. Thus, network flow techniques can be used to find the optimal load in this special case. The fact that generalized load balancing includes both these problems as special cases gives some indication of the challenge in designing an algorithm for it. Designing and analyzing the algorithm. We now developed an approximation algorithm based on linear programming for the generalized load balancing problem. The basic plan is the same one we saw in the previous section. We'll first formulate the problem as an equivalent linear program where the variables have to take specific discrete values. We will then relax this to a linear program by dropping this requirement on the values of the variables, and then we'll use the resulting fractional assignment to obtain an actual assignment that is close to optimal. We will need to be more careful than in the case of the vertex cover problem in rounding the solution to produce the actual assignment. Integer and linear programming formulations. First, we formulate the generalized load balancing problem as a linear program with the restrictions on the variable values. We use variables xij corresponding to each pair ij of machine I in M and job j in capital J. Setting xij equals to 0 will indicate that job j is not assigned to machine I, while setting xij equals to tj will indicate that all the load tj of job j is assigned to machine I. We can think of x as a single vector with m and coordinates. We use linear inequalities to encode the requirement that each job is assigned to a machine. For each job j, we require that the summations of xij, summing for all index I, is equals to tj. The load of a machine I can then be expressed as Li equals to the summations of xij, summing for all index j. We require that xij equals to 0 whenever I is not in mj. We will use the objective function to encode the goal of finding an assignment that minimizes the maximum load. To do this, we will need one more variable L that will correspond to the load. We use the inequalities. The summation of xij, summing for all index j, is less than or equals to L for all machines I. In summary, we have formulated the following problem. GL.IP is the minimization of L such that the summations of xij equals to tj, summing for all index I for all little j in capital J, and another constraint such that the summations of xij is less than or equals to L, summing for all index j for all index I in M. And the third groups of constraints are xij is chosen among the set either 0 or tj for all little j in capital J and little I in capital Nj. The fourth groups of constraint is set xij equals 0 for all little j in capital J and little I not in capital Mj. First, we claim that the feasible assignments are in one-to-one correspondence with the solutions X satisfying the above constraints, and in an optimal solution to GL.IP. L is the load of the corresponding assignment. 11.26. An assignment of jobs to machines has load at most L if and only if the vector x defined by setting xij equals to tj whenever job j is assigned to machine I and xij equals to 0 otherwise satisfies the constraints in GL.IP, with L set to the maximum load of the assignment. Next, we will consider the corresponding linear program obtained by replacing the requirement that each xij is in the set among 0 and tj by the weaker requirement that xij is greater than or equals to 0 for all little j in capital J and little I in mj. Let GL.LP denote the resulting linear program. It would also be natural to add xij, which is less than or equals to tj. We do not add these inequalities explicitly, as they are implied by the non-negativity in the equation. The summations of xij is equals to tj summing for index I that is required for each job j. We immediately see that if there is an assignment with a load at most L, then GL.LP must have a solution with a value at most L, or in the contrapositive. 11.27. If the optimal value of GL.LP is L, then the optimal load is at least L star, which is greater than or equals to L. We can use linear programming to obtain such a solution XL in a polynomial time. Our goal will then be to use X to create an assignment Recall that the generalized load balancing problem is NP-hard, and hence we cannot expect to solve it exactly in polynomial time. Instead, we will find an assignment with load at most 2 times the minimum possible. To be able to do this, we will also need the simple lower bound 11.2, which we used already in the original load balancing problem. That is 11.28. The optimal load is at least L star, which is greater than or equals to the maximum of Tj, where the maximum is taken among all possible index j. Rounding the solution when there are no cycles. The basic idea is to round the xij values to 0 or Tj. However, we cannot use the simple idea of just rounding large values up and small values down. The problem is that the linear programming solution may assign small fractions of a job j to each of the n machines, and hence for some jobs there may be no large xij values. The algorithm we developed will be a rounding of x in the weak sense that each job j will be assigned to a machine I with xij is greater than 0, but we may have to round a few really small values up. This weak rounding already ensures that the assignment is feasible in the sense that we do not assign any job j to a machine I not in mj, because if I is not in mj, then we have xij equals to 0. The key is to understand what the structure of the fractional solution is like, and to show that while a few jobs may be spread out to many machines, this cannot happen to too many jobs. To this end, we will consider the following bipartite graph g of x is equals to v of x and e of x. The nodes are v of x equals to m union j, the set of jobs, and the set of machines. And there is an hij in e of x if and only if xij is greater than 0. We will show that given any solution for gl.lp, we can obtain a new solution x with the same load L, such that g of x has no cycles. This is the crucial step, as we show that a solution x with no cycles can be used to obtain an assignment with load at most L plus L star. Now 11.29, given a solution xl of gl.lp such that the graph g of x has no cycles, we can use this solution x to obtain a feasible assignment of jobs to machines with load at most L plus L star in big O of m and time. Proof since the graph g of x has no cycles, each of its connected components is a tree. We can produce the assignment by considering each component separately. Thus, consider one of the components, which is a tree whose nodes correspond to jobs and machines, as shown in figure 11.11. First, root the tree at an arbitrary node. If the node corresponding to job j is a leaf of the tree, let machine node I be its parent, since j has degree 1 in the tree g of x. Machine I is the only machine that has been assigned any part of job j, and hence we must have that xij is equals to tj. Our assignment will assign such a job j to its only neighbor I. For job j whose corresponding node is not a leaf in g of x, we assign j to an arbitrary child of the corresponding node in the rooted tree. The method can clearly be implemented in big O of m and time, including the time to set up the graph g of x. It defines a feasible assignment, and the linear program gl.lp required that xij equals to 0 whenever I is not in mj. To finish the proof, we need to show that the load is at most L plus L star. Let I be any machine, and let ji be the set of jobs assigned to machine I. The jobs assigned to machine I form a subset of the neighbors of I in g of x. The set ji contains those children of node I that are leaves, plus possibly the parent P of I of node I. To bound the load, we consider the parent P of I separately. For all other jobs j not equals to P of I assigned to I, we have xij equals to tj, and hence we can bound the load using the solution x as follows. That is the summations of Tj summing for all j in Ji and j not in P of I is less than equals to the summations of Xij summing for all j in J without the restriction that j is not in P of I, which is less than equals to L. Now using the inequality bounding the load in GL.LP for the parent j equals to P of I of node I, we use Tj, which is less than equals to L star by 11.28. Adding the two inequalities, we get that the summations of Pij, summing for all j in Ji is less than equals to L plus L star as claimed. Now, by 11.27, we know that L is less than equal to L star, so a solution whose load is bounded by L plus L star is also bounded by 2L star. In other words, twice the optimal. Thus, we have the following consequence of 11.29. 11.30. Given a solution XL of GL.LP such that the graph G of X has no cycles, then we can use this solution X to obtain a feasible assignment of jobs to machines, with load at most twice the optimum in big O of mn time, eliminating cycles from the linear programming solution. To wrap up our approximation algorithm, then we just need to show how to convert an arbitrary solution of a GL.LP into a solution X with no cycles in G of X. In the process, we will also show how to obtain a solution to the linear program GL.LP using flow computations. More precisely, given a fixed load value L, we show how to use a flow computation to decide if GL.LP has a solution with value at most L. For this construction, consider the following directed graph G equals to VE shown in figure 11.12. The set of vertices of the flow graph G will be V equals to M union J, machine union jobs, union the singleton set V, where V is a new node. So we create a new node. The nodes little j in capital J will be sources with a supplied Tj, and the only demanded node is the new sink V, which has demanded the summations of Tj summing for all index j. We'll think of the flow in this network as load flowing from jobs to the sink V via the machines. We add an HJI with the infinite capacity from job J to machine I if and only if I is in Mj. Finally, we add an HIV from each machine node I with a capacity L toward V. Now 11.31. The solutions of this flow problem with capacity L are in one-to-one correspondence with the solutions of GL.LP with the value L, where Xij is the flow value along Hij and the flow value on Hit is the load, the summations of Xij summing for index j on machine I. This statement allows us to solve GL.LP using flow computations and a binary search for the optimal value L. We try successive values of L until we find the smallest one for which there is a feasible flow. Here we will use the understanding we gained from of GL.LP from the equivalent flow formulation to modify a solution X to eliminate all cycles from G of X. In terms of the flow we have just defined, G of X is the undirected graph obtained from G by ignoring the directions of the agencies deleting the sink V and all adjacent addresses, and also deleting all addresses from J to M that do not carry flow. We will eliminate all cycles in G of x in a sequence of at most mn steps, where the goal of a single step is to eliminate at least one edge from G of x without increasing the load L or introducing any new edges. 11.32. Let XL be any solution to GL.LP. Let C be a cycle in G of x. In time linear, in the length of the cycle, we can modify the solution x to eliminate at least one edge from G of x without increasing the load or introducing any new edges. Proof. Consider the cycle C in G of x. Recall that G of x corresponds to the set of edges that carry flow in the solution x. We will modify the solution by augmenting the flow along the cycle C using essentially the procedure augment from section 7.1. The augmentation along a cycle will not change the balance between incoming and outgoing flow at any node. Rather, it will eliminate one backward edge from the residual graph and hence an edge from G of x. Assume that the nodes along the cycle are I1, J1, I2, J2, I3, J3, and so on until IK, JK, where IL is a machine node and JL is a job node. We will modify the solution by decreasing the flow along all edges JL, IL, and increasing the flow on the edges JL, IL plus 1 for all L equals to 1 to 3 until K, where K plus 1 is used to denote 1 by the same amount delta. This change will not affect the flow conservation constraints. By setting delta equals to the minima chosen among all the possible XIL, where L is starting from 1 to K, chosen among all those K, we ensure that the flow remains feasible and the edge obtaining the minima is deleted from G of x. We can use the algorithm contained in the proof of 11.32 repeatedly to eliminate all cycles from G of x. Initially, G of x may have mn edges, so after at most big O of mn iterations, the resulting solution XL will have no cycles in G of x. At this point, we can use 11.30 to obtain a feasible assignment with at most twice the optimal load. We summarize the result by the following statement. 11.33. Given an instance of the generalized load balancing problem, we can find in polynomial time a feasible assignment with load at most twice the minima possible.